Hello again, grade 11s. I hope that you are well and that you are getting to terms with the power topic and the calculations. So, we're going to start off by going through the questions that you were given for homework, which was from exercise 24, number 18, until number 22. So, if we start with number 18, it's important in this question to realize, because there are two switches that are going to open and going to close, you need to understand where the current is flowing. So the first question asks you to calculate the resistance when both of them are closed. If both of them are closed, then we know that the current is going to flow through all the resistors. Okay, because it's all going to be closed, so the circuit is just going to act like normal. So if they want to know the total resistance, all we have to do is just calculate the parallel part of each one. So if I say, well, the parallel part of the first one will be 1 over R1 plus 1 over R2 to the negative 1. So that's going to be 1 over 12 plus 1 over 6 to the power of negative 1, which is just then going to be, if you put it in your calculator, you'll get 4 ohms. Okay, then if I look at the next one, I'm going to calculate the resistance of the second parallel component, which is the same equation. So that's going to be 1 over 3 plus 1 over 6 to the negative 1, which is going to be equal to 2 ohms. So then the R total will be the 4 ohms plus the 2 ohms, which is just 6 ohms. Then it says, what is the total current when both are closed? So if I want total current, I can start with Ohm's law and say, well, I total is equal to V total divided by R total. Now V total, I already know, that gave me was 12 volts. R total, I just calculated to be 6, so the total current is 2 amps. Now it says, what is the current in the 3 ohm resistor if S1 is closed and S2 is open? So now we must note that the current is going to be different in the sense that it flows differently. So the current now, S1 is closed, so it will go through both 6 and 12. But because S2 is open, the current will only go through 3 and it will ignore the 6 ohm, which means that if this is ignored, then the 3 ohm now goes from parallel to series. So if I want to know what the current is through the 3 ohm resistor, now because it's in parallel, then that is the total current again. So I'm going to make a little note of it, that the current through the 3 ohm resistor is I total, because the 3 ohm resistor is in series now. Okay, you don't have to write that, but I'm just making a little note of it so that you know. So I total again is V total over R total. Now the V total is still 12, that hasn't changed, but I don't know what the R total is. So the R total has changed. So I still have this series in parallel, which is the 4 ohms. But now that gets added to the 3 ohm resistor now because it's in series to this. So it will be 4 ohms plus 3 ohms, which is just going to be 7 ohms. So I'll say 12 divided by 7, which is 1.71 amps. Okay, so that's the resistance through the current through resistor 3 ohms. Then it says, what is the current supplied with both switches open? So now this has changed slightly now, where if both switches are open, then the current flows again differently. So the current, because the 12 ohm is open, it will only go through 6 ohms. And because the S2 is open, it will only go through the 3 ohms. So that means that these two resistors are then going to be in series with one another now. Okay, so it's important that you see, okay, well, they are in series together, so now you have to approach it differently. So because it's in series, then the current supplied is going to be I total again. And that's because it is a series circuit. So the I total in a series circuit is then going to be equal to V total over R total again. Now the V total I already know is 12. The R total I can figure out. It's quite easy to figure out the R total because the R total is just the two resistors added together. So it's the 6 ohms plus the 3 ohms, which is just 9 ohms. So if we take the voltage divided by the resistance, 12 over 9, we'll get the 1.33 amps, which is equal to the total current that goes through the circuit. Okay, so the power in the 12 ohm resistor and the 3 ohm resistor respectively when both switches are now open. So let's have a look at the 12 ohm resistor first. Does any current flow through the 12 ohm resistor? No. So that means that there can't be any current that goes through that resistor, meaning that there is no power through that resistor. So the power of the 12 ohm resistor is 0 watts. Okay, that's quite an important thing to take note of. Okay, so, and if you look at the equation, right, power is equal to I squared times R. Now, if I is 0, then the whole thing becomes 0. Okay, just so that you note there. Then if I want to know the power through the 3 ohm resistor, I can see, okay, well, does current flow through the 3 ohm resistor? Yes. Okay, which means that there is going to be a power. So I can use the same equation I used here. So I can say, well, power is I squared times R, which is the current I just calculated to be 1.33 times 3 is the resistance. So the power there is going to be 5.31 watts. Okay, so make sure that you go over these calculations. The main thing is to take note of what the circuit looks like when there's different flowing of the current. Okay, so if current flows differently, then it's going to affect the circuit differently, and it's going to transform one side to parallel from to series, or series to parallel, depending on what's happening. Okay, so put a star then next to question 18 and say that this is a nice exam question, okay, where you have switches opening and closing. Okay, then 19 and 20 are more of your application type questions. So these are like your level 3 or level 4 questions where you're going to be asked to interpret what is happening. So you have two light bulbs, X and Y, and you are told that light bulb, they have 40 watts and 60 watts each. So you are also told that the light bulb Y is glowing brighter than light bulb X. So one thing that I'm going to make note of here, because it's quite an important thing to note, is that power is directly related to the brightness. So when we talk about something having a high amount of brightness, then we imply that there is more power there. Okay, which makes sense because if something is going to glow brighter, it's going to use more power. So if I look at this question here, I can see that Y glows brighter than X, which means that therefore the power of y is greater than the power of x, even though I can technically see that because they said 60 watts and 40 watts. Okay, so because the power is greater in y than it is in x, I need to now compare. It says, how does the resistance compare of the light bulb y? And then to use an appropriate equation. So if I think about the power equations for resistance, okay, there are two equations that you could use. There is the one where it says P is equal to V squared over R. And we have the other one which says P is equal to I squared times R. Now, we are trying to compare the power and the resistance. Now, I need to figure out, I cannot compare these unless something is constant. So, something must be constant in order for me to use the equation to compare, like we were doing with Ohm's law earlier. So, if I look at the parallel circuit, which one is constant? Is it the voltage or is it the current? Well, I know that in parallel, the voltage stays the same, but the current splits. And because the watts are different, I know the current cannot be the same. So the voltage is the thing that stays constant. So I'm going to use that equation. So I will say, well, P is equal to V squared over R, but the V is constant. So therefore, P is inversely proportional to R. So if P is inversely proportional to R, it means that more power would mean less resistance. So therefore, the resistance of X is going to be greater than the resistance of Y. And that is because the power of Y is more, so the resistance of Y must be less because of this relationship. Okay, so just to reiterate, we establish that the power of y is greater than the power of x. Then we look at our two equations that compares power and resistance. And I try and find a constant. I is not constant, so I have to use this equation. That's why I use that equation. Now, if this is constant, I ignore it. And I say, oh, well, this is the same as 1 over r. P is 1 over r. Now, because this is inversely proportional, if P is getting bigger, R is getting smaller because they are inversely proportional. So that means the one with more power, which is Y, will have the less resistance, which is Ry. That's why Rx is greater than Ry. Okay, then it says the circuit below indicates the two light bulbs X and Y again are now connected in series. The light bulbs are still marked 40 watts and 60 watts. Light bulb X is shining brighter than light bulb Y now. Okay, so we notice now that it changes. Okay, where the light bulb X is going to be shining brighter than light bulb Y in this question. Okay, so we ask ourselves, why is that true? Why would the light bulb X be shining brighter than light bulb Y? So let's think about that. So we've already established that the resistance for R to the Rx is greater than the resistance of Y. Okay, we already know that from the previous question. So I'm going to say from 19. So now let's think about it. We are comparing the power again. So if we're comparing power and resistance, again we're going to use the same equations. But now So I'm trying to compare again P and R, P and R. But I notice that now the voltage is no longer the same because it's in series. However, I do know that the current is equal because the current is the same throughout the circuit. So I know that the current through X is equal to the current through Y, and P is equal to I squared times R. Now, because the current is equal, then I know that P is directly proportional to R. So if P is directly proportional to R and R has the greater resistance, then the power is going to be greater at X than it is for Y, which is why light bulb X is brighter. So it's important to remember that although we establish that power is related to the brightness, you must note that it also depends on whether or not it is in series or parallel. Okay, so that's also very important to establish as well. Okay, you cannot just assume that the power stays the same. However, we do know that power is still related to brightness. So that's why in this question, light bulb Y is brighter, but in this question, light bulb X is brighter. So it's very important in these questions you establish what you are trying to compare, two things. And then you say, okay, well, there's two equations that use those things. So go back to the equations and find the constant. And then you use the equation with the constant to compare, oh, well, because these are next to each other, they're directly proportional, but because these were opposite in the fraction, they are inversely proportional. Then you will be able to relate power to resistance in both of these questions and figure out which one is brighter. Okay, so now question 21. It says X and Y are two lamps. X is marked 12 volts, 24 watts, and Y is marked 6 volts, 18 watts. Calculate the current required by each when they work at the maximum potential difference. So if they're working at their maximum potential difference, that means that they're going to have that 12 volts and 6 volts each. So let's look at X. X, we'll use P is equal to IV. So the power is 24. The voltage is 12 and the current is I, which means the current is going to be 2 amps through X. If I look at Y, again I'm going to use P is equal to IV. The power is 18. The voltage is 6. So that means that the current is 3 amps. Okay, so that's the current required for them to work at their maximum potential difference. Then it says the two lamps are placed in the circuit as shown, with the battery having an EMF of 27 volts and insignificant internal resistance. The resistance are chosen, so X and Y will work at maximum potential difference. Okay. What would the reading on the voltmeter V be? Okay, so this is quite an interesting question to think about, right? Because the resistors are chosen so that the lamps X and Y will work at their maximum potential difference. So if I look at V, right, V is giving the reading over both Y and both X. However, if you look, there is this R2 here. So that means that Y is not going to get the total voltage V because it's going to be shared between these two. But the one that does get the total V is X because there's no other resistors here. So if I look at the question, right, X had a maximum voltage of 12, which means that the reading on that would be 12 volts, not 6 volts, because remember there's this extra resistor here which needs voltage. So the voltage here and the voltage here will be 12 volts, and the total voltage there is also 12. So just be careful of that, because this resistor is important. Okay, then it says, what is the resistance of R2? So if I think about Ohm's law, right, R is equal to V over I. Now, if the resistance R is equal to V over I, now I need to figure out, okay, how would I find these values? Well, I know that the voltage through Y is 6, right? Because they said maximum voltage. So the voltage here through this little Y is 6 volts, which means that the remaining voltage through R2 is going to be 12 minus 6, which is just 6 volts. So I know how much voltage goes through the resistor 2. Now, what is the current that will go through the resistor 2? Okay, so now this is quite an important reflection now. We've already established that if there's 6 volts of power through Y, that means that the current is 3 amps. Now, because the current is 3 amps through Y at maximum voltage, that means that it's 3 amps here as well. And because this portion here is in series with one another, that means that it's also going to be 3 amps through this resistor 2 as well. So that means that it's going to be 3. Okay, and that's because of this maximum potential difference that we've already worked out earlier. Okay, so make a star next to 21 as well, because this is also a very nice exam question. Okay, because it requires interpretation, which is an exam question. So then 6 divided by 3 is just 2 ohms. Okay, moving on. It says calculate the current through R1 now. Okay, so we're going to use the same method that we just used in the previous question. We know that there is 3 amps that flows through this portion. So let's see, well, we know how much flows through X, isn't it? Because we calculated that earlier, 2 amps. So we know that the current through X is 2 amps, which means that the total current will be those two added together. So the current through R1 is going to equal to 3 amps plus 2 amps, which is just 5 amps. Okay. The next question says, what is the potential difference across R1? So remember, we just established that this reading is 12 volts. If there's 27 EMF, that means that the remaining voltage will go through R1. So I can say, well, R1's voltage would equal to the EMF minus the 12 volts, which is equal to 27 minus 12, which is 15. Then it says calculate the resistance. Okay, hopefully this is quite easy because we have the current and we have the voltage. So R1 is equal to V1 over I1, which is going to be 15 divided by 5, which is just 3 ohms. Then question 22 says compare circuits M and N, identical batteries with negligible internal resistance. The light bulbs are identical. Which will the brightness of the bulbs in the two circuits compare? Okay, so you have these identical bulbs. One is connected in series, the other one is connected in parallel. So it's saying how will the bulbs in them in both circuits compare. So will the bulbs, it says the light bulbs M and N are equally bright. So they're equally bright here and here, since they're identical. Okay, the brightnesses are equally bright of M and M, since the batteries are identical. In M, they are both brighter, and in N, they are both brighter. So it's important to remember, because they are identical, their brightness will be the same in terms of in the circuit itself. So the brightness here is the same as the brightness here, and the brightness here is the same as the brightness here, because they are identical light bulbs, so they will have identical powers. So that's something to establish first off. Now let's think about what is changing in this circuit. Remember what we said, we have to look at the what's constant and what is something that is changing in order to compare. So power is equal to IV. Okay, that's the first equation. Then we also see power is equal to I squared times R, and we also see that power is equal to V squared over R. Now, if I compare now these circuits, what is changing is that the voltage stays the same. So voltage is not changing at all. So the voltage here is equal. Okay, what will change is the current. So current will change, and the resistance will change. Now, we can't then use this equation because there's no constant there. Everything is changing. So this one is out. So what I'm going to try and compare is, I'm going to either compare the P is equal to IV or the P is equal to V squared over R. Okay, so I know for a fact now, if I look at this, that the resistance of the light bulbs, the R total will change, but not the resistance of each light bulb. So if I'm looking at each light bulb, then this also stays the same. Otherwise, the brightness wouldn't change. So then technically this one is also out. So I'm looking at P is equal to IV. So if the voltage is the same, but the current is splitting, then power is directly proportional to the current. Now the current that flows through these light bulbs is going to be bigger than the current that flows through these light bulbs, because they will half. So if that is true, and they are directly proportional to one another, then I know that the brightness in N is going to be more than the brightness in N. So then the answer must be D, because the brightness by N will be brighter than M. Okay, because if we think about it, the current, the voltage here across, the total voltage is remaining the same, but the resistance is going to change. So actually, we can't use P is equal to IV. We would use the other equation. P is equal to V squared over R. So the reason for this is because the power is inversely proportional to the total resistance. Now, if I think about the total resistance here is higher than it is here. Which means that if the total resistance is more in circuit N, then the power is going to be more here because of this relationship that we've established there. Okay, the reason why we don't use P is equal to IV is because if we actually think about it, right, the voltage is the same, but the current through each light bulb is the same in each question, in the sense that, well, the current that flows through here is equal to the current that flows through there, and the current that flows through there is equal to the current that flows through there. Remember, we are trying to compare the brightness of each part. So what is changing is the resistance, and the resistance is what is going to change the current. So we can't look at the P is equal to IV because there's too many changes within the current. So the easiest way to look at it is to compare these ones again, like we have been comparing in the previous questions. Okay, so just take note of this because this is also another popular exam type question. Okay, then you can rule off, you can write the date, and the heading is going to be cost calculations. Okay, and the date would be the 14th of May. So now we're going to look at how we calculate the cost, basically, of electricity. Okay, so cost calculations is trying to calculate the cost of electrical energy transferred. That's what we're trying to calculate. So I'm going to make a note here. The cost of electrical energy transferred. So the cost of electricity is based on the amount of power used and the hours of power used. So what that means is, it means that we are trying to calculate the cost of electricity for electrical devices by first calculating the amount of energy that is transferred in the appliance and then multiplying that by the time that is used. So basically then we can say that the energy transfer if you can recall, is equal to the power multiplied by the time. So the W is equal to P times T. Now, the power in these calculations is always going to be kilowatts, and the time is going to be hours. And this is only when we are looking at calculating costs, and that's why we use kilowatts hour. Okay, so this is only specifically for cost calculations, but not for the other calculations. Okay, so the other calculations, it's still watts and seconds. In this case, it is kilowatts per hour. Okay, as a side note, remember that 1 kilowatt is equal to 1000 watts, and 1 hour is equal to 3600 seconds. Okay, so this is how we essentially calculate the cost of electricity. So if you look on page 139, you don't have to learn this off by heart, but on page 139 you'll find a table 1 with the amount of power electrical appliances use. Okay, so you use that table in order to answer the questions in the next exercise. Okay, but before we do that, I'm going to use that table and we'll go through the first example. So let's say that electricity is sold at, let's say, it'll actually be interesting to see the cost of electricity per kilowatt hour now. So if we actually look, so the average cost is between, so let's take the current average cost, which is at R1.82. So it's calculated at R1.82 per kilowatt hour. Okay, then we'll say let's use calculate the cost of running a geyser for 12 hours. So according to the table, it says that the geyser uses 2,500 watts of power. So the geyser uses 2,500 watts. So if I convert that, then it's going to be 2,5 kilowatts. So if I'm trying to now work out the cost, then I would say, well, the cost is equal to the kilowatts per kilowatt hour multiplied by the cost per kilowatt hour. So I would take the kilowatt hour, which is 2.5 kilowatts, for the hours. Now the hours that was used was 12 hours, multiplied by the cost per kilowatt, which was equal to 1.82. So we're going to say 2.5 times 12 times 1.82, which is equal to 54.6 Rand. Okay, so it would cost 54.6 Rand to run the geyser for 12 hours. Okay, so if you think about that, then if you multiplied 54.6 Rand by 2, you would get 109 Rand per day, because that's 12 hours, 24 hours would be a day. And then if you multiply that by 30 days, you would get to quite a high amount of electricity. And obviously that's because, remember that power, the geyser doesn't necessarily run at that full power of 2,500 watts for that full amount of time. It obviously switches off as you go. But essentially, if we just look at if it was running at that full 2,500 watts for 12 hours, that's how much Rand of money we would pay. Okay, so exercise 25 now talks about answering a table. So it says use table 1 if electricity cost is 65 cents per hour, per kilowatt hour. Now remember that cents and rands. If you want to convert from cents to rands, you would divide by 100. So from cents to rands. So if we were going this way, we would divide by 100, and if we're going that way, we'd multiply by 100. Okay, so it says the fan is 6 hours, radio 8 hours, kettle 1.4, a quarter of an hour, personal computer is 3.5 hours, microwave half an hour, and fridge 12 hours. Okay, so if I had to answer this table, so from table 1, I can get all the values for the fan and the radio kettle. So pause, go to the table and fill in the power. Okay, so the power for each one is going to be 70 for the fan. For the radio, it is 40. For the kettle, it is 2000. For the personal computer, it is 50. The microwave is 200. And the fridge is also 200. Okay, now it says, what is the kilowatts? So remember, the kilowatts is going to be the watts divided by 1,000. So the kilowatts will be 0.07, 0.04, 2, 0.05, 0.2, and 0.2. Then it says the number of hours that was used. So let's have a look. The fan was for 6 hours. The radio was 8. The kettle was for a quarter. Personal computer was 3.5. The microwave was a half. And the fridge was 12 hours. Now the amount of kilowatts hour would be the kilowatt, which is this one, multiplied by that one. Okay, so I would have 0.42, 0.32, 0.5, 0.175, 0.1, and 2.4. So the total amount of kilowatts hours that was used, you would just add all of these together, and you would get the total, which is 3,915. So that means that the cost is going to be 3.915, which is the kilowatt, multiplied, now it's 65 cents. So let's do 65, and we would put in your calculator, you get 254,475 cents. If you wanted it in rands, you would say divide by 100, and you would get, I think, sorry, it's not 254,000, it's 254. 3.915 divided by, multiplied by 65, yes, is 254.475. So if you divide by 100, you get 2 rand and 54 cents. Okay, obviously electricity isn't that cheap anymore. Okay, so then your homework is just then going to be to complete 1.2, okay, which you would use in a similar fashion in order to calculate the cost of running all these appliances for the amount of time that is allocated. Okay, so that essentially marks the last sort of information that we're going to go over in this section. So make sure that you go over all the previous questions and topics that we've already discussed, and then so the next time we'll just go over some of the exam questions, and then we'll look at answering those. Okay, so otherwise then, good luck. I hope that the whole of the circuits have made sense to you, and if you do need any additional help, then please either email me, go speak to Ms. Galliani, or you can wait for me to return, and then I'll go over a lot of the questions in an extra lesson. Okay, otherwise then I'll see you on the next one. Bye bye.